Welcome, everyone. Pleased to have you with us here today for This Is CDR. This Is CDR is an online event series presented by OpenAir to explore the range of carbon removal solutions currently being researched, developed, and deployed, and to contextualize them for policy proposals OpenAir is seeking to advance at multiple levels of government here in the United States, as well as in national and subnational jurisdictions globally. Everyone, please, if you haven't already, please introduce yourself in the chat and tell us where you're zooming in from. My name's Toby Bryce. I work on CDR policy advocacy and market development for OpenAir, and I'm based in Brooklyn, New York. Quick background on OpenAir. We're a distributed volunteer network dedicated to the advancement of carbon removal solutions that are essential to solving the climate crisis. We're a global community. We collaborate on shared open source missions in the areas of policy advocacy, research and development, and activist CDR market development. If you're not already on our Discord, there should be a link in the chat to sign up. Please join us. We organize our missions there, and we'd love to have you. We have lots of cool stuff to work on, and it's a lot of fun. Before we get started, just some quick housekeeping on definitional housekeeping and some background on what we mean when we say carbon removal. This definition here is from a work called the CDR Primer, which is a great open source peer-reviewed textbook for carbon removal. And this is also essentially the same definition the IPCC uses. Carbon removal is purposeful human activity to remove CO2 from the atmosphere and then durably store it in geological, terrestrial, or ocean reservoirs or in long-lived products. Two quick important things to call out when we talk about carbon removal. Number one, it's commonly conflated and confused in the media with quote unquote carbon capture, which refers to point source carbon capture, which means capturing CO2 from an emission source like a natural gas power plant or a cement plant, which may or may not be a good climate solution depending on the situation and the particulars. But one thing it's not is carbon removal. Carbon removal, again, is removing CO2 from the atmosphere and then durably storing it. Second, it's really important whenever you talk about carbon removal, and if you're working in the sector, to be very clear up front that carbon removal is in no way, shape, or form a substitute for reducing emissions. We need to reduce emissions and decarbonize our global economy as quickly and as completely as possible. Full stop. That said, there are going to be emissions that are difficult to abate or inequitable to abate. For example, emissions from the agricultural sector. We need to eat, and those are very difficult to abate. It's also, some countries in the global south are not going to be able to decarbonize their economies as quickly as the countries in the global north that are primarily responsible for the trillions of tons of CO2 in the atmosphere. And so for that reason, there's clear scientific consensus that we are going to need gigaton scale carbon removal by mid-century if we want to have any chance of reaching our climate goals of limiting warming to 1.5 or 2 degrees Celsius. That's billions of tons per year. Our current scale is thousands of tons per year. So we have a tremendous amount of work to do to scale carbon removal to get to the point where we need it to limit warming. And then in the second half of the century, there are many, many gigatons of anthropogenic CO2 in the atmosphere. And as we've seen, our climate is currently not in a safe state and it's going to get worse. So we're also going to need to remove the legacy anthropogenic CO2 that's in the atmosphere. And for that, both of those purposes, we're going to need carbon removal. We put a bunch of resources in the chat if you want to find out more. This is our 51st This Is CDR, so lots of great material on our YouTube channel. And today we have a very exciting presenter, and Megha Raghavan, my colleague from London, is going to hop on now and talk a little bit about run of show and then introduce today's session.
Hey everyone, I'm Megha. I'm an OpenAir member based in London and working on a bunch of policy advocacy opportunities both in Europe and in California. So the usual housekeeping notes. So our format will be a quick presentation followed by a few prepared questions, and then we'll have moderated audience Q&A. So please type any questions you have into the Q&A box in Zoom as we go along. If you can, just make sure you find the one that's labeled Q&A rather than the chat, so it helps us to organize the questions a bit better. And the event's being recorded, so we'll send the video link out to everyone who registered, as well as post it to OpenAir's website and YouTube channel. This week on This Is CDR, we're very pleased to welcome RepAir Carbon CEO Amir Shiner to tell us about the company's novel and energy-efficient electrochemical method of direct air capture, or DAC, which is inspired by fuel cell technology. Amir Shiner brings over 25 years of industry experience with startup and technology companies with a focus on developing and commercializing innovative products. He's co-founded RepAir with the vision of restoring the global CO2 balance by developing a highly efficient, sustainable, and scalable direct air capture solution. Amir earned a BSc in mechanical engineering from Technion, the Israel Institute of Technology. So whenever you are ready, Amir, feel free to put up your presentation and it's over to you.
Hi, thank you very much, Megha, and I'm really happy for the opportunity, and thank you for the opportunity to speak here today and sharing my presentation.
Yep, that works.
Again, Amir Shiner, CEO and co-founder of RepAir Carbon. We are a startup company located in Israel, developing an affordable, sustainable, and scalable direct air capture technology. Toby very nicely described why we need carbon dioxide removal technologies in order to really shift the business as usual graph from the 40+ billion tons per year to the 0 point by mid-century. This is not only a very important object from an environmental perspective, it is going to be a huge market opportunity by 2050. And we realize that. However, what we realize is that for the deployment of the conventional direct air capture technologies at scale, there will be a requirement of huge amounts of energy, and this might inhibit or limit the deployment that is so much needed globally. And this is exactly where RepAir comes into play. We at RepAir have been developing a technology that requires only a fraction of the energy that is required by other more established, I would say, direct air capture technologies with around 0.65 megawatt-hour per ton of CO2 captured, compared to around 2 megawatt-hour per ton CO2 captured by the more conventional technologies. And this technology is based on a novel electrochemical cell that separates CO2 directly out of the air. It's shown here schematically. We can see atmospheric air comes into the cell. CO2 depleted air goes back to the atmosphere, while pure CO2 gas streams out for storage or utilization. The cell comprises mainly of two identical electrodes and a selective separator in between them. If we zoom in on the cross section of the two electrodes and a separator, and we'll take a look at how this process works, we can see here schematically the two electrodes and the membrane between them, or the separator between them. And the process starts by applying electrical energy across the electrode and streaming atmospheric air through one side of the cell. Then CO2 immediately binds to hydroxide ions that are generated at the cathode side of the cell, forming bicarbonate ions that are then, under the electrical potential, driven selectively through the membrane or separator to the anode side, where the reverse process takes place, and those bicarbonate ions break back to hydroxide ions that are consumed by the anode, and pure CO2 that streams out as gas. So what we have here is a continuous separation process that is driven solely by electrical energy that will eventually, at scale, will come solely from renewable sources. Importantly, it takes place at or carries out at ambient or around ambient temperature, so no additional heat source is required for the process, and it's very modular and therefore will be relatively easy to scale. If we look at another image of that schematically shows the process, this is the air, those are the CO2 molecules in the air, and they are selectively driven through the separator from one side of the cell to the other side of the cell. We'll eventually stack hundreds of similar or identical cells to create stacks that can then form the modules that we will define as the building block for the technology, and then identical modules will be connected together to reach the required larger and larger capacities that will be required in larger and larger facilities. CO2, sorry, if I summarize the value proposition of our solution, first of all, it's an affordable solution due to the very low energy demand and the fact that we can use abundant low-cost materials for the technology. It is very sustainable since we power it solely by electrical energy that will eventually come solely from renewable sources. And it's very scalable due to its modular design and the fact that we use very low amount of liquids. And it's all translated, comes down to a projected separation cost of $50 to $70 per ton at scale. CO2 that comes out of the system will go either to sequestration or long-term storage or to utilization in products, for example, synthetic aviation fuel, cement, and some other products. The direct air capture market, as I mentioned, is a huge market opportunity. If we look at the projected carbon cost as published by the International Energy Agency and the amount the huge amount of carbon dioxide that will have to be removed by direct air capture, mainly by direct air capture technologies, is going to be a huge $1 trillion+ market opportunity by 2050. Until this market becomes more mature, the main driver of the market today is what's called the voluntary carbon market, with what we estimate is around $5 billion market opportunity at the moment, where what we see is global corporates targeting net negative by 2030, 2035, willing to pay premium prices for future offsets. A good example is Stripe Frontier that allocated around $1 billion for this cause, and RepAir recently signed an agreement with Stripe, a pre-purchase agreement to provide the first batch of CO2, the commercial CO2 that is going to be removed commercially, is going to go to Stripe. Just as an example of what this market is all about and how it can work to drive this industry forward. I'd like to mention that we've managed at RepAir to assemble a great, diverse, excellent team of scientists, engineers, technicians, entrepreneurs working together to realize our common vision. Just a glimpse at our R&D lab facility here in Israel, and as I said, I'm very proud of this excellent team that we have here. We're now at the process of closing around $10 million Series A funding. This will allow us to further accelerate our R&D and scale up activities with the objective to deploy the first commercial unit by mid-2025. Thank you very much for this opportunity. I'd be happy to answer any questions.
Excellent. Thank you, Amir. That was a great overview of RepAir. We always start by just kind of asking presenters a little bit about yourselves and your personal journey to carbon removal and direct air capture. Can you talk a little bit about how you came to the idea, how you got interested in climate, then carbon removal, then direct air capture, and maybe a little bit about how the RepAir came together and formed as a company?
Sure. I've spent most of my career in the medical device industry. What I liked about that field is the impact the product you develop and commercialize make on the lives of people. And then a couple of years ago, I met my partner, Yuda Bornstein, who was also on this call. And we sat over a cup of coffee. We met through a mutual friend. We started talking about this market. He started talking to me about the market need and the technology, the unique technology that he identified and I was kind of hooked up almost immediately with his energy, and his passion was contagious, and almost immediately I was with him on this journey. We shortly thereafter we incorporated RepAir and started moving forward very quickly. The more I read, the more I learned, the more I talked to people, the more hooked up I got about the need and the importance of really tackling this need. The RepAir technology emerged from the University of Delaware in the US. The professor who's been conducting a very extensive research over there on thermoelectric technology, and electrochemical technologies. Professor Yeshanyan is one of our co-founders, a partner here, and we signed an exclusive license to develop the products based on that technology here in Israel.
Excellent. Can you talk a little bit about two questions? Can you talk a little bit about how you came across the technology, from the University of Delaware, from where you're sitting in Israel, and then maybe also, in life, I've worked with a lot of tech companies in Israel, and it's such a vibrant, productive tech ecosystem. But I think you're our first Israeli company to come here on This Is CDR to talk about carbon removal. Can you talk about the Israel tech ecosystem from a climate tech and carbon removal perspective, maybe some of its advantages maybe that it offers, and any other companies from Israel that you're excited about in carbon removal?
Sure. My partner Yuda, who's a climate venture builder, identified this technology when he scanned for interesting, promising technologies to remove carbon dioxide directly from the atmosphere. And the dialogue with Yushan started, and they have known each other for years, working on fuel cell projects. And this is basically how it came about. Now, the environment here in Israel is a very good breeding ground for startups. Israel is very famous for its vibrant, high-tech software technology startup ecosystem. And this is due to several factors, starting from very good schools, very experienced people coming out of the military with the entrepreneurship spirit and the drive to succeed. I guess it has to do partially with the environment where we are located in the Middle East and our neighborhood, and the way we need to operate to survive and succeed here. So there's very good schools. People come out of those schools highly educated, highly motivated, and I think that's a key. There's a government support for early startups in the form of incubators and some other programs, and that helps early stage startup to start and move forward quickly, early stages. And then there's also a very vibrant VC community locally, and the international VCs that operate here, and international CVCs that operate here, and they are very involved in creating this ecosystem.
Excellent. Thank you for that. We're at OpenAir, we're big fans of and believers in modularity, and so it's always great to see presenters emphasize that in your product model. A friend of OpenAir, Naeem Merchant, who's a prominent carbon removal analyst, it was a while ago now, but I think it stood the test of time. He wrote a great post about modularity with respect to direct air capture, and he talked about three kinds of modularity: the form factor, so modular form factor, which you illustrated in your presentation, modularity of parts and using existing supply chains, not having to re-engineer every component of your system, and and finally, modularity of business model, really, focusing on capture or separation, as you term it, and partnering for storage or maybe utilization that you mentioned. Can you talk a little bit about how you look at that and whether that's reflective, those three aspects of modularity are reflected in RepAir?
Yeah, I think we apply to the three modularity aspects that you just described. In terms of form factor, we base our system on identical electrodes, identical cells, and then identical stacks and modules. This will allow us to move from the lab to serial production and to mass production relatively quickly and easily, building supply chains and relying on existing supply chain and production infrastructure. And that's key. And that's key in order to drive the capital cost down, which is, we talked about the energy consumption, but the capital cost is another major challenge with direct air capture. And when you look at producing identical modules at scale, at very large sizes and very large numbers using sophisticated production lines, this is going to be something very important in order to bring the cost down. And this also brings me to the modularity of working with partners, not only storage and not only storage partners, but also production partners. It's very important to partner with the right strategic production partners and create the right supply chain that can support you in the long haul. And this is something that we're going to do it in RepAir. We're going to remain focused ourselves on the core technology and to work with relevant partners that we already started identifying and working with on the key elements in the technology and also the peripherals of the systems, project, EPC, and so on.
Excellent. Thank you. Another analyst, Peter Miner from Carbon 180, talked about DAC 2.0 and a vision of DAC 2.0 kind of moving beyond sort of the first generation of direct air capture companies. And his three elements were modularity. He talks about the same ideas that Naeem talks about, moving beyond chemical sorbents, which I think your fuel cell model obviously does. And the last one he talked about was air contact and passive air contact specifically, but minimizing the energy requirements of the air contact. Can you talk a little bit about how you handle the air contact? I wasn't clear on that from what you were presenting.
Yeah, of course, any direct air capture technology has to mobilize large amounts of air through a system. Since we're talking about 0.04% of carbon dioxide in the atmospheric air. So in order to reach the capacities, we need to look at very large amounts of air. And we need to bring this air in contact, in our case, in contact with the electrode in a way that CO2 will then bind to the hydroxides that are generated at the electrode. So we bring a lot of air in. We design the airflow system in such a way that will minimize pressure drops. This will minimize the energy consumption of the fans of blower that we're going to use to drive those amounts of air in. So we have on one side we have innovative airflow design to minimize pressure drops. On the other hand, we have an innovative electrode design to reach the maximal or the optimal surface area to really allow for a maximum efficiency of the process of binding the CO2 molecules from that air and then taking each molecule from one side of the cell, shifting it to the other.
one other kind of sort of functional economic question. Obviously, you live in a relatively hot, arid environment. Is there a specific environmental conditions that your systems are best suited for? Can they work in any system? Is it better in a hot, arid environment? Is more moisture better? Can you talk a little bit about how those different factors might affect performance?
Yeah, our process requires some humidity, so we need to control the relative humidity at the cell environment. We're now currently working around 70 to 80 degrees relative humidity. We're going to moisturize the air as it goes in, and to control relative humidity, the relative humidity window. So we need to add some water. So depending on the region of deploying the system, in hot and humid regions, such as equatorial regions, we might not need to humidify the air. We might be able to rely on the existing air humidity, and whereas in cooler regions, we might need to implement humidification and dehumidification elements in the system. And of course, we took that into consideration when designing our lab and then our commercial systems.
Got it. Thank you. Switching gears a bit, when you think about your deployment and scaling, is there a particular form factor that you are finding to be, at least theoretically, optimal? Do you think about megaton plants? Do you think about a more distributed deployment with smaller systems? How do you think about that, and what makes the most sense from where you're sitting right now and sort of time and everything else?
Taking into account that we are still early, but when we look ahead and we try to project or try to plan 5 steps or 10 steps ahead, the way we look at it is we look at it at a more distributed approach due to energy supply constraints and some other considerations. So we don't envision like a 1 megaton plant, rather say 10 to 20 smaller plants of 50,000 to 100,000 tons per year capacity, distributed over 10 to 20 different locations, depending. I'm talking about sequestration for now. So depending on the various locations that will have to be identified and prepared. So 50,000 to 100,000 ton sounds reasonable and makes sense to us.
Can you share a little bit more of the reasoning behind that scale versus megaton scale? Is it that, have you reached the needed economies of scale once you get to that size? Is it like, what is it, capital requirements? Like, what makes you kind of focus on that? Or is that kind of an intermediate step between potentially where you are now and a larger scale?
It can be only an intermediate scale. That's how we look at it right now. But for example, when I look at the energy that will be required to power a 1 megaton scale plant in one location, is going to be a huge amount of energy. Okay, and we'll need to have a good, reliable, continuous supply of energy, and this can be a constraint for any direct capture facility. Okay, so that has to be taken into consideration. Then, footprint is another consideration. It's not the most, perhaps not the most critical one, but it's also something that we need to take into account. Also, some social aspects. Distributing smaller plants can better support social objectives of governments. Okay, I know, for example, that in the U.S. the direct capture hubs have been, the government has looked at distributing the hubs in such a way that will support shifting or creating jobs that are, called the jobs of tomorrow, rather than, shifting people from the jobs in the oil and gas industry to the climate industry, okay, in areas that need it most. Just an example of considerations.
Yeah, no, that's great. And I appreciate the realism about land use and energy requirements, which is not universal, I would say, out there. So thank you for that. Two more questions, and then we're going to switch to the audience questions. We're getting some good ones. Everyone, please keep those coming, and Megha will be on in just a second to pose those to Amir. One, just back to your distributed deployment notion. One of the distributed deployment opportunities that OpenAir is particularly excited about is DAC and concrete. That may not reach to the 50 to 100 kiloton scale, depending on it. I don't think an individual concrete facility would potentially need that much CO2, but is that a market that you've looked at potentially as a way to scale up? And one of the reasons we like it is because it is utilization, but it is utilization that results in durable storage of the CO2 as opposed to a more circular use. Can you talk a little, is that something you've thought about? And if so, how do you look at that opportunity?
This is something we've thought about, obviously, exactly for the reasons that you just mentioned. This is not only utilizing CO2 for products, but also can be considered a long-term or storing the CO2 and then allowing the potential customers to get incentives for that. For using it for concrete. So this is something we've been looking at seriously. I have to say that the limiting factor, not only for us, but for the entire direct capture sector, is scaling up. So we're very much focused now on scale up, and once we reach the meaningful scale, we will start working with potential partners. It can be storage partners and can be utilization partners, and we're kind of keeping our options open to those two vectors that might require slightly different business models, but that's okay. And the concrete is definitely one of the leading utilization opportunities.
Got it. Thank you. One last question. So another thing we think about a lot at OpenAir is how we can build a just and equitable carbon removal industry, and very much appreciated your alluding to that issue when you were talking about your scale up plans. Can we just drill down into that a little more and talk about, in addition to the benefits that the potential commercial development benefits of scaling direct air capture, meaning jobs and benefits to the local economy and tax base, what other issues do you think about? Are there other benefits? Are there any negative externalities to your process that need to be addressed with nearby communities? It'd be great to hear a little bit about how you as a company are kind of thinking about these issues and how you plan to incorporate these ideas into your scaling strategy.
Yeah, well, we're deploying large-scale facilities will require some land and will require building a plant. Okay, so in our case, what we look at is the opportunity to minimize the effect that those plants are going to make on the immediate and more distant environment. Since we are going to operate our process using renewable energy only, and since we don't need any additional heat source that will come from any, waste heat or residual heat, our impact on the environment, on local communities is going to be very minimal. We're looking at something, a plant that is fully electrical, that is basically clean, that will not require large amounts of water, that will not produce any waste, that will be kind of blended in the environment as much as possible. And to this end, we've engaged with, we retained the services of industrial designers, and we're going to work with them on how to build a facility that will blend in the environment in a way that its impact will be minimal.
Got it. Okay. Thank you so much. Megha, are you there? And do you want to hop on and start asking some audience questions?
Hey, yeah, sure. So we got a couple of questions on just the impact of things like pollution and particulate matter. So people mentioned dirt, dust, PM 2.5, sand, smoke from forest fires. So how do those different kind of particulate sizes affect your membranes, and what can you do about that?
Well, we're going to incorporate a certain filter, straightforward filtering, depending on the needs locally, and that is already taken into consideration when we look at the pressure drop, energy consumption of the system.
Okay, got it. And in your system, just again on the membranes, is it only AEM anion exchange or anion exchange membranes that you use, or are there other ion exchange membranes involved in the process?
No, only that.
Okay. And then the same person also asked if water is an inlet stream for the hydroxide ion, what other byproduct streams come out of that?
Say again, sorry.
If water is one of the inlet streams that produces the hydroxide ion, what other byproduct streams are also produced, if there are any?
No other byproducts. We have some humidity, as I said, in the air, and the process is highly selective. So only those bicarbonate ions cross the membrane from one side to the other side of the cell. Okay,
got it. Another question we got, I guess, thinking a little bit about others who are doing, similar DAC process. Someone asked, how does this compare to the Verdox system, which was developed at MIT? Is your product or your process different in any key ways that you would want to point out?
Well, it's different. Of course, what Verdox is doing is very interesting. We believe we have a couple of advantages that I would summarize in, a more straightforward, easier to scale approach.
Okay, got it. Okay, and then in terms of the overall energy estimate, someone asked, how does your estimated overall energy estimate compare to the minimum thermodynamic energy of separation, which they put for the number of 420 VPPM of CO2?
Yeah, we are slightly higher than that, and we've been working, and there's a potential to further reduce the energy consumption of the process, and this is still a work in process here in the lab, and there's still potential to further reduce our energy consumption to get closer to the minimum that you mentioned, and even I think I know even of an even lower number that you just mentioned.
Okay, and could you maybe talk about some of the key levers or drivers that you think can bring down energy consumption in a process like yours, or in DAC more generally?
Well, I'll talk about our process. Energy consumption is driven by the what we call the capture rate of the process, meaning how much CO2 we can capture per given cell area. The more we capture, the better we are, and we've been working to improve that around the clock with very promising results so far. So really optimistic that we will further improve that. Another important factor, as I mentioned earlier, is how you handle the air, and this is again something that we've been focusing on greatly, designing innovative cell stacks that will, on one hand, bring the air in the flow rate, the right flow rate, and the right conditions, and on the other hand, will result in a minimal pressure drop.
Okay, got it. And then I know Toby asked a little bit about concrete as like a usage that could be one sort of destination for the CO2. Could you talk a little bit more about other opportunities for CO2? They asked about liquid fuels, but anything that you have in mind?
Yeah, one good example is synthetic aviation fuel, SAF. I think we're all familiarized with the carbon engineering 1.5 degree and their plan to produce synthetic aviation fuel in commercial quantities, and this is really interesting. Since this is a very hard to abate sector, I mean the aviation sector, and it will take decades, I believe, until we see large aircraft operating on electric engines or motors. So, and this is something. This is a field that is really interesting, and we've been looking at it closely. Although we believe it will take a few years until the processes of producing synthetic aviation fuel, not only the CO2 is only one element, but you need hydrogen and you need some other processes, and you need and the industry will have to mature those processes such that this synthetic aviation fuel becomes economical.
Okay, and are there any other use cases for the utilization side outside of fuels that you guys are looking at?
Early on we looked at greenhouses in something that we'll get back to when we reach a more meaningful scale, and this is something that has been evolving as well. So greenhouses is an existing market. Also, it's a relatively small, but it is an existing market that has been using CO2 to enrich the atmosphere of the greenhouse, to improve the yield and shorten the cycle time. And with the global food crisis, this has become even more important in the last couple of years. So this is something that we'll consider as well later on.
Okay, great. Someone actually asked, would this technology be something you would use at point sources where there's a high CO2 concentration, or does this make more sense, as the sort of atmospheric carbon capture that you've been sort of talking about?
Yeah, theoretically, it can be with several adaptations. It can be used for point source as well. However, we strategically decided to focus on carbon dioxide removal, at least for now, and it's not going to change in the future.
Okay, got it. And then how do you think, since you were talking about it being a modular system and there might be quite a distributed locations of different plants, how do you think about the storage side of things and getting the CO2 to, potentially more centralized storage sites?
Well, the beauty of direct air capture in general is locating the plant at the point of utilization or storage. So we will do our best to avoid any transportation of CO2 for both costs and emissions. And so the idea is to work with potential storage partners on storage locations that will make sense depending on the scale. And that's on one hand, and then work with customers, potential customers later on utilization sites again to place or deploy the system in proximity to the location where it is going to be used.
Got it. Just do a couple more on the sort of technology side before asking a little bit more on economics and things. So someone asked, is your process a continuous capture system, or does it work in batches?
It's a continuous process. As I said, we operated on electricity, and basically a continuous process.
Okay. And then thinking about the electricity side of things, you're talking a little bit about the importance of building enough or having enough energy capacity. Is that something, the renewable energy requirement, is that something that you plan to build out yourself? Or do you think that that Israel is building up a renewable grid that can serve the purpose that you need?
First of all, we're looking at ourselves globally, not necessarily in Israel at scale. Okay, so we'll definitely work with energy suppliers, renewable energy suppliers, and storage to ensure a high quality, consistent supply of energy that will be needed in order to run those plants almost 24/7.
Okay, got it. Great. I think switching over to sort of the commercial / policy side a little bit. So you mentioned a target price of $50 to $70 per ton. Can you just talk a little bit more about how you kind of arrived at that figure and how you forecast where the price will end up?
Well, first of all, this is projected at a megaton scale. Okay, mm-hmm. So all our projections are made assuming that the deployment reaches a megaton scale, and we relied on Department of Energy reports on scaling up fuel cells, and since this is in a way similar technology. We could at least partially rely on reports that look at scaling up fuel cells. So we kind of borrowed several data points from those reports, and then we looked at the International Energy Agency projections and some other projections, and we made some assumptions based on recently published papers. And we looked at our trend of developing the technology and running it forward, and we based on all that we reached our estimation.
Okay, great. And then what are kind of the biggest levers you think are going to drive the cost down from whatever they're like today to what you see it being at the megaton scale? It's on one hand improving or optimizing as I said, the capture rate and airflow design in order to keep the energy consumption as low as possible. And on the other hand, is reaching the production scale that will allow us to work with the suppliers on reducing costs. And we already started discussing with potential suppliers of key elements in the systems. And we already see that when we look at larger sizes and larger quantities, the price, the cost of certain key elements in the system drops exponentially. Got it. Okay. And then thinking a little bit more about the policy side, I know you mentioned potentially expansion beyond Israel, but could you just talk a little bit about the appetite for, CDR or climate policy in general in Israel, and what kind of the state of that is like at the moment?
As you know, Israel is a small country, is smaller than New Jersey, and so we are in the global. From a global environmental perspective, we are very, very small, but we are kind of a powerhouse for developing technologies, as I said earlier. So Israel is looked at as I said as a place where solutions, startups should come out from, not necessarily. The first country to implement, the most advanced, renewable energy and so on. Although in recent years, Israel has discovered and developed new natural gas reservoirs and deployed very advanced concentrated solar power systems in the Negev desert, in the southern part of Israel, and deployed large solar PV farms in the south. But it's basically a powerhouse of testing innovative technologies that can then be taken from Israel to expand to other locations.
Got it. Makes sense.
I think a good example is a company called SolarEdge, that is originally, still is an Israeli company, is one of the global leaders of solar PV panel suppliers.
Got it. Okay, great. We got one new question on the technical side, so I'm just going to do that and then one last one after that. So the question is the expected lifetime of the collection modules known yet, and are there degradation or contamination issues to worry about from the airflow?
Yeah, we target 10 years for the modules. Since we work at very mild conditions, low temperatures and low current densities, and based on the experience with certain batteries, which use similar materials, for example, nickel, that we use for our electrodes, we believe that this is 10 years is an achievable target. And then for the entire system, I mean, with the auxiliary equipment, we target 20 years, which is an acceptable number in the industry.
Perfect. Okay, great. Last question before I hand us back to Toby to close up. What kind of government policies would best help to accelerate your work and, maybe more generally the CDR space? And if you have seen it, where in the world are you starting to see the policies that would make you want to expand there?
Well, we look at the incentives by the tax incentives by government as one key element in the long haul. In the short term, we believe that governments should go hand in hand with the entrepreneurs and the pioneering companies to support the early development of innovative technologies. And we've seen that in Israel, we've seen that done in Europe by the European Commission. We've seen that in Scandinavia. And I think what we've seen recently in the US with the IRA is really important to further develop larger projects and deploy larger systems. So the US is starting to do recently has been really encouraging.
Okay, great. Well, that's it for the questions. So thank you so much. It's been super interesting for me. And I think definitely from the chat, there's a couple of people who want to get in touch with you. So we'll make sure to put that in touch. Thanks so much. And Toby, on to you.
Thank you.
Thank you very much.
Sorry, hold on. Thank you, Megha. And Amir, thank you. That was a really excellent presentation. And thank you for bearing with us through so many questions, some of which were pretty specific. So we really appreciate your time and sharing what's going on with RepAir with us. And we wish you the best of luck in your next steps in terms of scaling the business and closing that round of financing.
Thank you very much. Thank you for the opportunity to present here today.
And Amir, before you sign off, you might want to just check the chat. There were a couple of people who wanted to get in touch with you that might be interesting for you to connect with. I put your email into one of them.
Thank you so much.
Cool. Thanks again. And the last question is kind of a perfect segue into a really important priority for OpenAir right now. We're really focused on, in North America, advancing government procurement policies for carbon removal. We have a live state level bill in the state of New York. We also have state level bills that are soon to be introduced in Colorado and Massachusetts. So if you're in the audience and you happen to live in either of those states, please get in touch with us because we need citizen advocates for both of those policies, again, in Colorado and Massachusetts, as well as in New York. And then finally, if you live in North America and the US, there are 2 federal carbon removal bills that will get the federal government, in addition to the 45Q tax incentives that are in the IRA that Amir referenced, that will actually create government procurement programs for durable carbon removal, just like Frontier is doing, which will be incredibly impactful. One of the bills that we are doing a nationwide citizen lobbying effort for is the federal CDRLA, which was introduced by Representative Paul Tonko from Albany, New York, and Scott Peters from San Diego, California. There's a companion bill in the Senate. So if you live in the U.S., would love for you to join our effort. We're getting new representatives to co-sponsor the bill. I would say almost weekly now, just through this project. So it's making a difference. So please, if you're not a member of OpenAir, please follow the link in the Discord to sign up for OpenAir, and please help us with this work. We have more This Is CDRs coming. We'll be announcing new episodes soon, so stay tuned to that on our Twitter. We also send out a weekly email with all of the programming. But thank you so much for being with us. Thank you again to Amir for such a great presentation, and everyone be well, and we'll see you again soon.